Good morning, afternoon, or evening. How y'all doing today? Welcome back to Morals Math Corner. Today we're going to learn how to work with, write, and solve direct and inverse variation problems. So let's get right to it with a real-world example. The time it takes to hear thunder varies directly with the distance from where the lightning strikes. This is modeled by y equals 1/5 x, where y equals the distance in miles of the lightning, and x equals the time it takes to hear the thunder after seeing the lightning strike. So let's say you're at home looking at the night skies, or on a hike looking up at the night skies, or just looking ahead of you, and all of a sudden you see lightning strike, and you count for 5 seconds and you finally hear the thunder. Well, when you plug those 5 seconds in, you're going to realize that the lightning is 1 mile away. If you count for 10 seconds before you hear the thunder, then that lightning is 2 miles away. If you count for 15 seconds before you hear the thunder, then that lightning is 3 miles away, etc., etc. And that is a direct variation example. A direct variation is a relationship that can be represented by a function in the form of y equals kx, where k cannot equal 0. The constant of variation, k, for a direct variation is the coefficient of x. Remember that the coefficient is the number being multiplied in front of another variable. So in this case, the k is the coefficient of x. And if you solve for k, you're going to realize that k equals y divided by x. You can determine whether an equation represents a direct variation by solving for y. If you can write the equation in the form y equals kx, where k does not equal y, then it represents a direct variation. Some direct variation concept summaries. Y varies directly with x when the function is in the form of y equals kx. The x increases, the y increases then by the same factor. Number 3, when the x decreases, the y decreases by the same factor. And number 4, when the k is constant and not being added or subtracted to another number or variable. Let's look at an example. Do the given equations represent a direct variation? If so, find the constant of variation. Well, for a here, let's solve for y. So we're going to divide 7 to both sides. Y equals 2/7 x. This is a direct variation because nothing is being added to that, and my k is the coefficient of x, which is 2/7. B, I'm going to go ahead first and subtract 4x to both sides, leaving me with 3y equals negative 4x plus 8. Divide by 3. And if you notice here, y equals negative 4/3 x plus 8/3. That's going to throw a wrench into this problem. So no, this is not a direct variation. Example C. Let's go ahead and subtract 4x to isolate the y. Now we're going to go ahead and divide 5 to both sides to solve for the y, and y equals negative 4/5 x. So yes, that is a direct variation, and my k is the coefficient of x, which is negative 4/5. And for my last example here, we're going to solve for y by dividing negative 3 to everything on the other side, leaving us with y equals negative 2x plus 3. And once again, this plus 3 is being added to the kx value there, so no, this is not a direct variation. Now suppose that y varies directly with x, and y equals 35 when x equals 5. I want you please to write the direct variation equation that models the situation, and then using the direct variation function you just created, solve for the value of y when x equals 9. Now don't overthink this, don't stress out. Step by step. We know that they're telling you that y varies directly with x. So that means that y equals kx. Then they gave you a y value of 35. We don't know the k, but they did give you an x value of 5. So let's go ahead and solve for our constant of variation, our k, by simply dividing 5 to both sides. Now we know that k equals 7. So my function, my direct variation function, is y equals 7x. That's the function, because what's really important here is the k. The x can be anything it wants, and then we can solve for y. And vice versa. We can choose any value we want for y and then solve for x. But the 7, the k, that's the constant. That's what we're looking for. So this right here is my function. Now I can go ahead and use that function and solve for y when x is 9. So what is y when x is 9? Well, let's simply plug it in, and y will equal 63. And it's that simple, but please follow the steps. Next, remember that if the constant of variation k is the same for each pair of data, the relation is a direct variation. Determine if the following relations represent a direct variation. Well, remember that if it's a direct variation, you're working with y equals kx, and therefore k equals y over x. So the easiest way to determine if this is a direct variation is to see if y divided by x is constant throughout. And 6/4, when we reduce it, is 3/2. Oh, that's a little bit messy there. 3/2. 12 over 8, y divided by x, again when you reduce, is 3/2. 15 y over 10x, when we reduce, is once again 3/2. So my constant of variation k is the same here. Y divided by x is constant here. So yes, this would be a direct variation. How about the example B? We've got 3.2 divided by -2. Well, that's going to give me -1.6 over 1. All right, let's look at the next y over x. Well, this one is 2.4 over 1. Wait a second, we can stop right here. -1.6 over 1 and 2.4 over 1 are not constant, so no, this is not a direct variation. It's that simple. Divide y divided by x, and if they are constant, it is a direct variation. Now let's examine inverse variation. With inverse variation, the same concepts apply to inverse variation, except that the x varies inversely with y now. And the function for inverse variation would be y equals k divided by x. And when we solve for k, k would equal y times x. Remember that k is the constant of variation, and k cannot equal 0. K is always the anomaly that we're looking for. That's the value that really makes the function. Now, what about joint and combined variation? Joint variation occurs when several factors are being multiplied to the k. Once again, k is the crux of the function. That's the important part. So when you have something like y equals k x z, the x and the z are being multiplied to the constant k, that's called joint variation. Multiple variables are being multiplied to the k. And combined variation occurs when k is being both multiplied and divided by different factors. So for example, y equals k times x times z divided by w. The x and the z are being multiplied to the k, and the W is being divided to the K. So when you have both multiplication and division relating to my K, the constant of variation, you have what's called combined variation. Let's look at an example. The weight W that can be safely supported by a 2-inch by 4-inch piece of lumber varies inversely with its length. So let's write that situation right now immediately. W varies inversely. So that's K divided by L. How do you know that, Moro? Well, W is the Y in this case, and it varies inversely with the length L, which is the X in this case. Experiments indicate that the maximum weight a 12-foot pine 2x4 can support is 400 pounds. So let's do some analysis right now. The 12-foot pine, that's my length, and the 400 pounds, that's my weight, W. Find the function that relates the maximum weight to the length L for any pine 2x4. Okay, so the W that they gave us in this case is 400. We're just going to plug in to the situation that we formed up top here. Okay, we're just reading and plugging in. So the W, 400, equals K, which is the anomaly right now. We don't know that. And our L is 12 feet. So how do we solve for K? We're going to go ahead and multiply 400 times 12. We get rid of a denominator by multiplying. So K will equal 4,800. So now I know my function. We know that regardless of the weight, the W, it's going to equal 4,800 divided by the length L. Remember, what stays constant is the K. The W and the L are variables that can be manipulated. So now we're going to determine the maximum weight that a 15-foot pine 2x4 can sustain. So now they've given us a length of 15. That is my L. So let's plug it in and find the maximum weight, which is what they're trying to determine. So W equals 4,800 divided by a length of 15. And when we do that math, we divide 4,800 by 15, we find that the maximum weight it can sustain is 320 pounds. Always remember to label units. All right, this is real world stuff. Determine whether the given relation is a direct variation, inverse variation, or neither. Little hint for you. Remember, if it's direct variation, remember that direct is y equals kx. So that means that k equals y over x. If we have an inverse variation, we've got y equals k divided by x, so k equals y times x. So let's check. If it meets the standard of k equals y over x, it's a direct variation. If it meets the standard of k equals y times x, it's an inverse variation. So let's first start with direct. 15 divided by 2 is 7.5. 7.5 divided by 4 is not 7.5. It is 1.875, so we can stop right there. We know that it is not direct. All right, now let's check for inverse. 2 times 15 is 30. 7.5 times 4, x times y, is once again 30. 3 times 10, which is x times y, is 30. And 2 times 15, x times y, is once again 30. So my constant of variation here is y times x. That's what's constant. So this is an inverse variation. And it's that simple. Okay. Let's get a little bit more complicated here. Suppose that x vary and y vary inversely. So right off the bat, immediately, you know that y equals k over x. Why do you know that, Mr. Morrow? Because they tell you that x and y vary inversely. So an inverse variation is k divided by x. And x is 4 when y is 12. Find and write a function that models the inverse variation. Well, we were given a y of 12. We're looking for our k. We were given an x of 4. We're going to go ahead and solve for k by multiplying 4 to both sides. So therefore, k equals 48. And there you have it. My function is y equals 48 over x. And there's the function. All right, now some real life situations. The force F of the wind on a flat surface positioned at a right angle to the direction of the wind varies jointly, that means repeated multiplication, with the area A of the surface and the square of the speed V of the wind. A wind of 30 miles per hour blowing on a window measuring 4 feet by 5 feet has a force of 150 pounds. What is the force on a window measuring 2 feet by 6 feet caused by a hurricane force wind of 100 miles per hour? Let's look at the first information because that's the most important. They tell you that F, the force, so we're going to start with the force, that varies jointly with the area A of the surface and the square of the speed of the wind, which is velocity, but it's the square, so squared. And now we know it's jointly, so that means that we're going to have to multiply a k to that. So we have joint variation. Remember that that's a repeated multiplication to the k. So now, the wind that they gave us was 30. So we know we're going to have to square 30. The area they gave us is a 4 foot by 5 foot. So the area is 4 times 5, which is 20. K is what we're missing. And the force that they're giving us here is 150. So let's first solve for k. So we've got 20 times 30 squared. 30 squared is 900 times 20. So that's going to be 150 equals 18,000 K. We're going to solve for K by dividing by 1800, and K will equal 150 divided by 1800, and K will equal 0.0083 repeating, and we can convert that to a beautiful fraction of 1/20th, 1/120th. So the force equals 1/120th times the area times the velocity squared. That's my function. Okay? Now it seemed complicated, but you and I both know that it wasn't really that bad at all. Just follow the steps. Now let's go ahead and move this over here, the work. And now let's use our function to find what we need to find. We want to find out what is the force on a window measuring 2 feet by 6 feet caused by a hurricane force wind of 100 miles per hour. Well, we're looking for F, the force. Now it's going to equal 1 over 120 times the area. 2 by 6 is an area of 12. Times the velocity of 100 miles per hour squared. So we're going to have 12 times 100 squared divided by 120, and the force would equal 1,000. And there you have it. And force is always represented in newtons, which is represented by a letter N for newtons. All right, pretty cool. The electrical resistance of a wire R varies directly with the length of the wire L and inversely with the square of the diameter of the wire D. So right off the bat, we know that R varies directly with the length of the wire L and inversely, that means dividing, so we have a combined variation here, inversely with the square of the diameter. So let's plug in and find the K and write our function. If a wire 432 feet long, so that is my L, so let's plug that in, and a 4-meter diameter, so we got 4 down here squared, has a resistance, which is the R, of 1.24 ohms, find the resistance in the wire that is 282 feet long with a diameter of 3 millimeters. So first things first, let's solve for K. So we've got over here 1.24 equals 432K over 4 squared, which is 16. We're going to go ahead and multiply by 16. And that's going to give me 1.24 times 16, which will equal 19.84. And we're going to go ahead and divide that by 432. Now you could have just multiplied by the reciprocal, of course. And K will equal a pretty large decimal of 0.0459, but we're going to round our answers to 2 decimal places. But before we do that, we can go ahead and convert that long decimal using our calculator into a fraction of 3160 over 675. So my function here is R, the resistance, equals 31 over 675 times my L divided by my D squared. So now let's answer the question that we're looking for. We want to know the resistance. We want to find the resistance in a wire that is 282 feet long with a diameter of 3 millimeters. So the resistance here will equal 31 times my length of 282 feet divided by 675 times my D diameter of 3 squared. So let's go ahead and do that math. We got 31 times 282 divided by 675 times 3 squared, which is 9. And that is going to give us a resistance of 1.316. We want to round it to 2 decimal places, so that will equal 1.32 ohms. That is the measurement for resistance, ohms. So that will be OHMS. And there you have it. Hope you learned a lot. Thanks for watching and come back anytime. Take care now. Bye-bye.